Okay, welcome everybody from my side. And my name is Sasha Lazarevic. On behalf of Quantum Serbia, what I'm showing on the screen is the announcement of our event. It's the 22nd event since the beginning of our group, Quantum Serbia. So this group gathers the people in the field of quantum computing from Serbia, Serbian expatriates, and all our friends. So we are doing the events mostly in English. Our communications are in English, so because we are really open to all friends who would like to join it so that we can learn about quantum technologies together. We have regular events online, sometimes also offline in different locations, mostly in Belgrade, in Serbia, but we'll see if this can be expanded in the future. We are present also in LinkedIn. We have a LinkedIn group and Slack channel for those who really want to intensively to exchange and to do some initiatives and projects around quantum computing. And also YouTube channel. So this event is being recorded and is going to be posted in YouTube channel Quantum Serbia. Feel welcome all of you to search our previous events. You will see there are quite a lot of interesting things that happened in the last 4 years already. So we have really great pleasure today to have Stanislav Protasov from Riverlane today with us, who is going to talk about something really which is so important that we cannot imagine the use of quantum computing for any of the practical problems, and this is quantum error correction. And this is very relevant also, especially as this talk is coming from Riverlane, which is one of the leading companies in this field. I had the pleasure to start reading, like we're not finished, but I started reading the report from Riverlane that was issued in October last year. It's really wonderful report. I invite everybody to check this on their website. And also Stanislav is, I had pleasure to meet Stanislav also last November in Belgrade, where he gave a speech about quantum error correction during the Q-Tangled conference in November in Belgrade, but it was a very short event. It was 30 minutes. And thank you, Stanislav, for accepting to come back and to talk about this topic. But we are really looking forward how you're going to expand on that and to explain it a little bit better, what is it and how this, where we are now. So we are going to get also the update of with the latest information. So Stanislav is a software engineer at Riverlane. This is a Cambridge-based scale-up that specializes quantum error correction. Not only that, he is associate professor, machine learning and knowledge representation at Innopolis University. He has rich background in academia, specializing in different aspects of high-performance computing, machine learning, information retrieval, and quantum computing. So it's really wonderful that we have you here. And Stanislav is really, he's a wonderful speaker. So you'll recognize he has very good approach. He's enthusiastic about sharing his knowledge. He also wrote a math book for programmers. So I'm going to stop sharing this screen here. And I invite you, Stanislav, to show us your slide deck and to guide us through that. And for everybody, please keep yourself muted so that we have a clear voice and we can understand well. And use this chat to ask the questions at the end of this event. Or Stanislav, I don't know if you would like that we stop in the middle, like to see if
I think that the organization of the slides is that in the end of each chapter, I will have a slide for questions, and we will have the oral communication because I will be sharing. I won't see your faces, so you will be able to ask me questions in person, like with voice. Okay.
Okay. So if this event is small like this, so we can have a really more intensive and dynamic conversation among everybody. You may also enable your cameras if you want to ask questions in person like that. Okay.
Okay, let's go. Are we ready? Yeah, I'm sharing my full screen, and you should be able to see my slides now. Yeah, good. I'll try to, okay, and I can also try to use the laser pointer to sometimes point somewhere. Okay, so my name is Stanislav Protasov, or just in short, you can call me Stas, and I will be giving you a very multi-level view on quantum error correction. So I still have kind of a small assumption that you are aware about what quantum computing is, and I will be building on top of this. Probably if you have any basic questions on quantum computing in general, you may ask them in the first sections, but I'll try to avoid relying strongly on quantum computing, and I will be speaking about this particular area of the domain. Okay, so what we will be speaking about. So we'll start with the motivation. So we'll start with why do we need quantum error correction? So why this term actually is important today, and why it's the main way to build a useful quantum computer. Then I will give you a very informal introduction in QC, quantum error correction, and say how the appearance of quantum error correction in the practical domain, so in real life, in real QPUs, when we start running the code on quantum computers. When I use the word QPU, I mean quantum processing unit, the quantum computer. So how it changes the hardware. Then I will try to go through kind of open challenges and say what has to be done to get the fully useful quantum computer in the end. And if we are lucky to be quite fast, so I can go through the topics which are more they're deeper in terms of theory, but they are, again, so they are not very necessary. And as I hope there will be a chance to distribute the slide deck, you will be able to download, and probably we can attach the slide deck to the YouTube video. You'll be able to go through them yourself if we don't have time for this. So let's start. And the first question, the biggest question, why on earth we need quantum error correction? And we will start with the citation from John Preskill, the American quantum computing expert and a professor, who was saying 7 years ago that there is a term, noisy intermediate scale quantum, which more or less addresses the devices which we have right now. So these are noisy, not a very big scale. It means dozens or maybe small hundreds of qubits. And these devices can exist, and they can be a useful tool for solving some physical problems, probably quantum physical problems. And these computers can become more and more useful as soon as we make our quantum gates, the primitive operators, the smallest possible building blocks of programs, to make them work better. And then by improving this quality of particular gates, we can achieve the fault-tolerant quantum computing, which means that we can assume our quantum computers are that reliable as we think about our classical computers right now. So we don't expect a classical computer to run a program probabilistically, right? So you run a program, you run it again, you expect to get the same result. So this is what we think about fault-tolerant quantum computing as well. And this was the guess of 7 years ago. And it was quite a consensus among the companies that, yeah, this is the way we should go. We build medium, intermediate scale devices, and we try to improve our gates. And of course, at that time, the theory of quantum error correction already existed. And the companies who were building hardware were put in front of the choice. Should they accept this paradigm, the noisy intermediate scale quantum, and be happy with hundreds and potentially thousands of qubits which they can put inside a single fridge and make them work as a whole, and then can achieve some benefits, maybe some commercial advantage, and pursue this way? Or think about theory which says, oh, to have a really fault-tolerant computer, you probably need to add redundancy. You have to replace one qubit with a like a group of qubits. Each like small circle here represents a real physical qubit, and this all is a one logical qubit. So if you introduce redundancy like this, you'll probably have to have millions of qubits, right? And then your computers will be really reliable. And when you have to make a choice, you definitely prefer to take the choice which is cheaper for you. And there was a reason to have this kind of an optimism that NISQ will work. So this graph is from the Riverlane report, which Sasha mentioned in the beginning of the talk. So we have this link here, and the link to the report will be in the end in the form of QR code. You can scan it. And these graphs, they show that with each year, if you look on the top graph, the amount of error we can observe on each primitive operation, each gate, goes down. So our qubits are becoming more and more reliable. And at the same time, with each year, for all the platforms, for all the technologies we use for built-in quantum computers, for neutral atoms, ion traps, for superconducting qubits, for silicon qubits, we grow the sizes of our systems. They become bigger. Some of them becoming bigger faster. Some of them are slightly slower, like ions. Ions are not very scalable, but superconducting are growing like exponentially in terms of size of the chip. And this optimism is on this graph. You see that, they are getting better. We're having them like more of them. Why cannot we just rely on the fact that physicists may bring this error down even more? Like this scale is exponential, so it will be 10 to the minus 4, 10 to the minus 5. Probably this is the reason. But you may also observe that some of these graphs are starting becoming like more flat, and the behavior is slightly, there's some variance in the behavior in the last years. And the kind of the latest, I think, last year and this year, I already heard lots and lots of kind of arguments for following the NISQ strategy. And I think ion traps companies are the last who defend noisy intermediate scale quantum era, who said that actually you can do computation on just bare qubits, on the bare ions. So each ion will become a single qubit, and that's okay. So the recent paper from Oxford Ionics was showing that you can do like a very, very low error. You see it's like much lower than what you showed on the graph, 10 to the power of minus 6. Quantinum basically says, oh, we achieve 3 nines. So it's like, again, very, very like low error, very, very high quality of qubits. At the same time, one of the founders of IonQ recently gave a talk, and he was showing that in principle, using I think they use the Ytterbium qubits, which IonQ uses, can get you up to 10 to the minus 11, which is extremely good. But the problem is in the control hardware. So it's not in the qubits, it's in all the equipment you use to control those qubits. And this is the last citation is from this year. I took it from the Quantum Art, the Israeli ion trap company, who's saying that as we targeting to do good qubits, basically, we don't care which strategy you would like to do. Would you like to do error mitigation, or would you actually do a quantum error correction? So we are agnostic to this. We think that we can have useful computers without quantum error correction. So these are the arguments. But at the same time, almost like a year and a half ago, in the end of 2023, the same person, John Preskill, at one of the talks he gave at the conference, he actually pointed that all the evidence for the last 5 years by that time, so since 2018, that noisy intermediate scale quantum computers can be useful, can do some commercial value, all they failed, or at least were not very convincing. And that's why we should change our paradigm and start building computers with error correction, because this is the only way to get fault-tolerant computing. So you see this fault-tolerant computing appears again in his citation in the end. So, but in previous slide, it was mostly reliant to the fact that we want to build the better qubits. Now he says, oh, you see, the better qubits can be achieved only by introducing redundancy and having like logical qubits, which are basically the bunches of physical qubits working together as the whole. And to understand why, if qubits cannot become better, so why QEC, quantum error correction, can still help us. This is probably good to start with a major theoretic, like a pillar of QEC. It's called the threshold theorem. It's a statement which says that if we understand quantum computers pretty well, so if we understand how they work, then we know some schemas, some algorithms of introduction of redundancy into systems. So taking multiple qubits and making them work together as a whole. And if we can do this, then the quadratic growth in the size, so let's say you have a page like 5 by 5, then 6 by 6, 7 by 7. So this type of growth exponentially suppresses error. So which means that if you drop some qubits into your logical qubit, make it bigger, then your error, the logical error, becomes significantly less. So you can observe this on the plot. So if you draw a vertical line here, so like follow the red pointer, you will see that if you have, let's be here, if you have a distance 3 code, so it's 17 qubits. So if you stand on the physical error rate of 10 to the power of minus 3, you have the same logical error rate, 10 to the minus 3. So there is kind of a balance. You whether use the logical qubit or you whether use the physical qubit, they have the same quality. But if you go down and you say, oh, you want to introduce distance 5, which is 5 by 5, so like 49 qubits. So you now have 10 to the power minus 4 logical error rate with the same physical error rate, right? So you go one order of magnitude down in logical error. So you can suppress errors much more efficiently. And if you go down even more for distance 7, which is like around 100 qubits, so you get to 10 to the power of minus 5. So by like dropping more and more physical qubits into logical one, you reduce the error by an order of magnitude. And when we speak about the threshold theorem, it's about this vertical line, which is like a dashed line, which says that, oh, if your quality of qubits is beyond threshold, so if your quality is worse, so it's like 10 to the power of minus 2, or like it's 1%, or even more, then unfortunately those codes don't work. So with the amount of qubits, they become even worse. So what we are interested in going below threshold, so our quality of physical qubits should be around these numbers. And then by introducing redundancy, we can hope like more and more. And of course, you see that the gap between the lines grow bigger, which means that the better is the physical error rate, the better is the scalability, the better is response for redundancy. You put more physical qubits into a logical one, and then it's becoming even better. So the gap becomes like not an order, maybe like 2 orders of magnitude. So this is the theorem, and this theorem, of course, needs proofs. Kind of probably this one is kind of covering the topic of terms. So threshold, as I mentioned, is a physical error rate. So the quality of your physical qubits below which we can apply quantum error correction and benefit from it. So if you go beyond, if you go to the right part of the graph, things become much worse and you don't benefit from it. You don't use quantum error correction. And there's a pseudo threshold. It's a diagonal line, which I also show you on this graph. So if you have this like dot here on the line, so the physical error rate and the logical error rate is the same. So there's no preference which qubit to use, whether to use redundancy or use just a single physical qubit, the error rate is the same. So your redundancy doesn't help. And crossing this bar, crossing this like diagonal line when the physical error rate and the logical error rate is the same, is called crossing the pseudo threshold. So when your logical qubits start behaving better than physical ones, and it's kind of sometimes even more challenging task. And this is the screenshot from the paper of Google, I think 2 years ago, when they first time showed that they could cross this, and their redundancy schemes, they actually are beneficial. And this blue dot is beyond the diagonal line. So then let's move to the practical point. I'm speaking about quantum error correction. But as I said, the final goal we want to achieve is fault tolerance. So the quality of our quantum computers to behave like perfect ones, as our classical computers, when you give it a program and it deterministically executes it with a predictable result. For fault tolerance in quantum world, you probably will find one of those metrics, one of those qualities in numbers, which give you more or less understanding of whether we accept this computer as useful or not. So these are like the one which is top, I think the ancient one called the quantum volume was introduced by IBM or adopted by IBM and slightly changed. And they say, okay, so we say with this width is the number of qubits, and this depth, it's the number of operations. So the program, which is kind of the smallest of two, and it's successful in 2/3 of outcomes. The algorithmic qubits, which are introduced by IonQ, they say, oh, we want to run on n qubits, the program with depths of n square operations, and be successful in 30% of our outcomes. Okay, a reasonable metric, which says that this is kind of okay. For Riverlane, I think this is kind of, now we try to widespread this term, and I think that John Preskill is also using this term now, which is very optimistic, is that we want to say that we want to measure in the final number of operations. We actually are very close to those previous definitions, but we say, well, let's multiply n by d. Let's say we have this number of qubits and this number of operations done on each qubit, and this number should target 10 to the power of 12. Let's be like the first mount for us is to do a tera co-op, tera, so it's 10 to the power of 12 quantum operations co-op. And you can apply this metric for both quantum computers and to programs. So you can measure the depth of the complexity of the algorithm in these co-ops, and you can measure the ability of quantum computer to execute those programs, right? So you can use the same metric for both programs and computers. And in this corner picture, which is a screenshot from one of the papers, you can see that there was a research where people took some algorithms from quantum chemistry and also from cryptography, and they tried to assess them in terms of co-ops. So how many logical qubits you need, what's the depth of your circuit, how many operations you want to execute, and you have those numbers. So gigaco-ops, teraco-ops, and some teraco-ops. So it's, of course, teraco-op in this particular case means that we won't be able to run the very bottom algorithms, but we target this. This is our first useful part, because in this case, we will be able to solve first two problems, right? So this is the way how we measure the quality. And we say that, in terms of Riverlane, we assume that quite an acceptable fault tolerance is around 10 to the power of 12 logical operations being executed without errors or with reasonable probability of an error. So let's do a checklist, and I'm open for your questions. I will make a small pause. So what terms did we come through? The fault tolerance means that the quantum computer operates very reliably, and we can run a program without thinking about error correction. NISQ and QC, NISQ, noisy intermediate scale quantum. It's the current market of physical quantum computers we have. They are noisy, they are quite small, and they're quantum, okay? And quantum error correction is the way how to take those noisy computers and try to convert their qubits into a reliable logical qubits by taking 100 of those physical qubits and converting them into, let's say, one. The threshold theorem is the theorem about when this scheme is useful. So if you don't achieve the desired quality of the qubit, then you cannot use quantum error correction. And teraco-op is something which you can use to assess the quality of computers and algorithms and to see how far one from another. Any questions?
Stanislav, I would have a question about this slide where you showed these qubit error rates for different modalities.
Mm-hmm.
I see here these dashed lines. Are they kind of estimates, or they are something that, I mean, where are these points coming from? Do you know anything about it?
Very good question. I have no idea. But I know that these like lines, the dashed ones are for neutral atoms, right? The only one is neutral atoms. And this is one of the kind of the newest technologies. And I think that the reason we have this line, I actually I didn't read the report like very precisely, is that the whole market was afraid of neutral atoms because they are behaving very similar to ions. So you see the ions were the oldest technology which appeared. And neutral atoms appeared like a decade ago, like almost 2 decades ago. And they started catching up very quickly in terms of error rate and in terms of like quantity, right? So they're growing very quickly. They are, I think, quite easy to navigate. So like for ion traps, you hold them in the electric field and they usually are like a chains of atoms. So they are like in a very particular order, while neutral atoms are currently what I know that for QR, for example, they are allocated as arbitrary configuration. So if you have a saw like the shows when drones are painting in the sky, let's say they're drawing like the same you can do with qubits. You can fly the qubits, which are neutral atoms, in any direction, in any configurations, and do it simultaneously. It's like easier to control. You cannot achieve this with ion traps, and that's why I think this projection is showing that they are, like at least by 2024, they were meant to become the leading technology in both quantity and quality. That's my kind of interpretation of this.
Yeah, thank you. Anybody else?
Okay, let's run.
Sorry,
Yeah.
did you mean the neutral atoms are meant to be, or the trapped ions meant to be the best technology?
It's not like it's still a competition. Ion traps are kind of, as I mentioned, they showed like since the report was released and until now, this few months, I saw quite a few, I think, statements from ion trap companies saying that, oh, we can actually do much better. And at the same time, the people who work in ion trap companies, they, at least what I heard from my colleagues in this field, they were quite worried about successes of neutral atoms because neutral atoms came the latest, but they're showing the best improvement performance. So they are like the amount of qubits you have inside their systems is already hundreds, and they can do very similar things to ion traps. But I think that they have some other problems which are engineerily kind of solvable. And ion traps are afraid of neutral atoms. That's what I know from the last months.
So neutral atoms, there are actually companies making quantum gates, quantum chips using that, or is that just research?
No. Like one of the, I think the biggest company is called QEra. You can.
Oh, okay. Thank you.
Yeah. I think that one important thing is that, yeah, it's a very good question. So when I speak about building a quantum computer, what I mean is probably I don't consider universities as qubit builders, even those university groups which do in-house development, which do like the build quantum computers, they still try to spin off into something like a startup because they need like a strong kind of income of money to support their research, which is bigger than you can get from the government, like through the grants. And let's say there are still groups in universities which can show like a very good machines. But for example, like in Europe, we worked with Technical University Delft, and they have only 17 qubits compared to what Google have and so on. They are like far behind. And like university groups are usually not on par with the commercial companies who can like attract more money from venture investors on their research. So for any technology, I probably can try to name the company which is the most successful, and it's still a company, not a university. So if you go for neutral atoms, it's QEra. For ions, this would be IonQ Quantinum, I think, these two. For superconducting, these are Google, IBM, and Rigetti. these three. Yeah, for photonics, it's Anadu from Canada. Yeah, they're all companies. They're not universities.
Stanislav, there is
Yes.
also slide 9 where you have these charts.
Mm-hmm.
I think it's number 9, I don't know.
This one?
No, it was the other one where you have the threshold. Yes,
Mm-hmm.
this one. So this D here is a degree of redundancy, or what is
Yeah,
that?
you can consider as a degree. So it's the number which you have to square and multiply by 2. Let's say it's the simplest interpretation to get there. So in this case, you will do D squared will mean the number of qubits you allocate for representing the logical state, and you will have to have the same amount of qubits or similar amount of qubits to represent the ancillary qubits, the like additional who will do parity checks for you. I will show you this a little bit later. So these numbers, you can, if you square it and multiply by 2, it will give you a rough estimate of how many qubits you will need for one logical qubit.
Okay, thank you. Okay, if there are no questions, I think we can.
Oh, otherwise we will stuck on this slide. So let's speak about what is QEC. So quantum error correction is a technology, kind of an area of study. It's quite a big area of study inside quantum computing, which originated from classical error correction. The idea was to, as literally on a compact disk, to represent some state with with more data, with some redundancy, and you use many physical qubits to represent kind of a logical qubit, and you do kind of this correction by introducing parity checks, the same way you do, for example, for parity bits in classical computer science. And there are many schemes which can be implemented. So I will be showing mostly pictures of one of these, but you may assume that these configurations may be multiple. So, but unlike in classical error correction, you cannot like swipe through all the bits and check their states, right? When you want to correct an error, you cannot read everything and correct as you can do in a classical system, because when you read in quantum systems, you destroy the state. So you need some smart trick which can help you to understand what's the state, what are probable errors, without actually reading the state of the system, without reading the data which is encoded in quantum computer. So what is done is that you have the orange qubits here, which represent your data, which is kind of your redundancy in code. But also you have one like this. One is actually many of them, this blue qubit, the number 5, it's sometimes called ancillary qubit, which is doing a parity check with this smart circuit. So what happens is that you put this qubit in superposition, and you do basically parity checks. So you do controlled gates. Sometimes it's CZ, sometimes it's C0, based on the code. And then you like move back to the computational space. And if nothing happens, if all those states were okay, nothing happened, you should expect that this qubit will return back to its original state, or otherwise it will flip, right? So it will obtain, if one qubit got corrupted, it gets, for example, the bit flip. This bit flip will propagate through the entanglement gate, and you will observe this in a parity check. If 2 got flip, then you don't see it again. If 3 flip, you see again the parity check, the same way you do parity check in the classical codes. So what we need, we didn't know these parity checks can be implemented. So this is at least one of the schemes you can do. And then you need algorithms, which will, based on these parity checks, so it's kind of a very implicit information, correct the logical errors which happen to your data, and try to understand what could lead to this configuration of parity, and try to correct back the data qubits if it's needed. So what is important about quantum error correction in terms of hardware? So I spoke about like theory a little bit. So it's about the practice. That when you think about quantum computer, it's a very weird device, because you know how to input into a quantum computer, because you have a control system. It's like a box which can do some laser pulses or like magnetic fields, and you know how to like introduce information into the system. The system is a very like complicated one. It has a very high dimensional space, computational space. You can do very smart and clever things inside this space. But in the end, you will end up having, again, the classical information. You'll have to read out the states in classical bits, which collapse the whole beautiful space of quantum into a classical space. And you probably heard about quantum computing that these like 5 qubits, basically, they represent 2 to the power of 5-dimensional Hilbert space, while when you read out, you have 5 bits of information, only 32 bits, so 32 possible states. And this is kind of always a painful part of quantum computing. So what you would like to do, you would like to postpone collapse of those interesting and very capable quantum space until the end of computation. You do everything you need there, and then you read out the important information, the answer for your problem, right? And if you open the textbook on quantum computing, almost all the algorithms they will look literally this way. So you do lots and lots and lots of gates, and in the end you read them, all the qubits, and you interpret the result. Either you read it as a number, or you're interested in histogram distribution of those values, no matter, but you read in the end, right? Quantum error correction brings you some problems. And one of the problems is that you will have to measure those parity checks during the computation. So not at the end, but while you're doing computation, you have to collect those classical information to be able to process it and correct the state of your quantum computer. And these mid-circuit measurements are very hard. The measurement is like if you take the superconducting computers, it's the longest operation you can imagine. So it's usually like 1 or 2 orders slower than any other gate. And a lot of QPU, like quantum computer producers, they don't even think about the fact that they have to read out during the computation. So they never introduced these mid-circuit measurements. And these are this is a continuing conversation. So this is, in my experience, I'm now talking to the second company who is doing superconducting qubits and say, oh, we don't do mid-circuit measurements. So we cannot do quantum error correction at scale. We can only do a very small experiment, which has the one readout in the end. So what else? Kind of random facts without any order is that even if you can resolve all these technical issues, in the end we have to come up with a very obvious thing. So we know how to do gates on a single qubit, like on a ion or like a Josephson junction, but we have to like scale this up to logical qubits. So if you say, oh, these 50 qubits will be now my logical qubit, I'll have to do the same gates I can do on a small qubit on this patch as well. I have to do C0 between these 2 patches. I have to know how to do Clifford gates, or at least I have to do T gate, be able to do a T gate, or like arbitrary rotations if it's possible. And these logical gates should be compatible with an architecture, because you have to obey the fact, for example, that on a superconducting computer, you have the planar allocation of qubits. So they are like a chip, they are plane. So you cannot easily connect the qubit which is distant from the other qubit, right? The same way you cannot do the distant gate on a physical gates as well. So you have to obey the architecture of your QPU. And next is that the algorithms, which will try to correct, so which will consume parity checks and return corrections for your quantum computer, will have to work in a very high pace, because if we speak about superconducting computers, quantum computers, this circuit from the previous slide, this circuit, will be executed within 1 microsecond. So the characteristic time would be for Hadamard gate, it will be like 20 nanoseconds. These are some dozens of nanoseconds. Altogether with measurement, it will take below 1 microsecond. It will be like 3 orders slower for ion traps, but it's still like not a huge time, millisecond. And you have to do all the classical computations under this budget, because otherwise you'll have a backlog. So you do computations on a quantum computer and you collect the problem of error correction, and you are not capable to correct those errors, and you will have to correct them like for a long time after the program is finished. So this is kind of useless. And yeah, the checklist and questions, probably not very organized chapter. So quantum error correction codes are ways of organizing multiple physical qubits into a logical one. And they are usually like considered, not all of them, but many of them considered as a combination of data qubits, which hold the logical state. Let's say one is all zeros is zero, all ones is one. Okay, so you try to operate on this. And ancillary qubits, which perform parity checks, which are measured every 1 microsecond. And this classical information is transferred to a decoder, a program, or a hardware, which try to look at them and say, oh, I see that your logical state got corrupted. Please apply additional X gate back on your qubits. Decoders are classical algorithms, and lots of research in quantum error correction is actually done in the sphere of classical algorithms. That's probably the most surprising thing for me when I joined this company. Then if we go to a physical quantum computers, when we try to take this theory and bring it down to hardware, you will see that mid-circuit measurements and qubit resets are extremely hard problems, and not many of the QPU providers were thinking about those problems. And the last is that it's not only enough to collect qubits in the group, you have to make them work as a whole. So you have to execute logical operations on them. You have to do NOT, you have to do like controlled NOT, you have to do all the operations you can do on a single qubit on this patch as a whole, right? Questions, comments?
Yes, please, questions.
Okay, I assume I lost a couple of speakers, listeners already. No questions? Or
I will have one.
okay.
What is actually the challenge, I mean, to perform this mid-circuit measurement?
I will speak about this a little bit later if you don't mind.
Okay. No problem. Yep.
Let's go further. I have not many time. So let's speak about what are the challenges actually, what has to be done, and try to answer Sasha's question. So let me introduce 4 personas, like 4 people. These are actual people, I know them in real life. So which work in different areas of quantum computing, but they are all working in the context of being aware of quantum error correction. So previously they could do whatever, but now they say, okay, we live in the paradigm of quantum error correction, and we have to do quantum chemistry, we have to do QEC research, control engineering, and like do qubits, keeping in mind that we are doing them for quantum error correction, right? So what are those challenges? So let's take Maria, who is doing qubits, who is like building the physical systems. So the qubits currently are on the QEC threshold. If you remember the plot where like the graphs were going down, so some of the technologies they just crossed this bar, and you remember that if you can go significantly below this threshold, then your improvement with additional qubits will be more and more sufficient. So if you can move from like 1 per million to 10 to the minus 4, you will have you need much less qubits to achieve the same logical fidelity, the same logical error rate. And being able to get there is still kind of the most challenging task. So making qubits work better is just hard. There are fabrication reasons for this, because you cannot do perfect things in real life. There are fundamental limitations. For example, the one which was discovered a couple of years ago, but then resolved, was related to the cosmic rays. So when Google was making an experiment, they observed that they cannot move below some particular bar, and they had no theoretical explanation for this. It appears to be that the cosmic radiation was a significant factor, and some highly energetical particles, they were hitting into their chip, which is quite small, but it was enough to have one in a million of those operations to change the results of the experiments. They found the way how to overcome this, but it was a fun fact that there are some, you have to consider lots and lots of fundamental physics to get there. So each qubit type has its own pain point. So for example, so when you control ions and atoms, and you want them to work together, so you want them to perform operations, being entangled and interact. So then they are usually like moved by like tweezers, so laser tweezers. So you just hold them in a beam of light, and you move them. And currently, you can lose an atom or an ion, and so you can slip and it just disappears, right? So you don't have it, and it ruins the whole experience of computation because you don't have this object anymore. You cannot read the information from it. You don't know where it is. You have to like reload the new one and restart the computations. So superconducting circuits are fixed, so you cannot lose a part of the circuit. It's very hard, but you can have a fabrication defect. So if you have like let's say a grid 10 by 10 of qubits, and when you made a defect, it can be like just a fabrication defect in the middle of this grid, and you will have the perfect connectivity, let's say like all 4 nearest neighbors, but one inside will be just, misfunctioning, and like it will affect the neighboring qubits, and this will be kind of probably a significant problem. I think that sometimes I saw diagrams from IBM and from Rigetti which show this, which show that, this for this particular qubit, let's say everything is an average is okay, so it's the 95% of CX control not gate quality, but this particular qubit behaves like 60%. And you cannot do anything. Just you already fabricated this. It's a very expensive work. So you have to find out the ways how to deal with fabrication defects in your computation. So they all need a perfect cold and vacuum, and they need to be calibrated. So when we speak to some customers, they say, "Oh, if you want to do a computation, please schedule us a meeting. We will calibrate the device for your connection. So we will connect and run on a calibrated device. It will drift from the calibrated state very quickly, like in an hour. And you have to do the experiments in a very like allocated time slot. And in a day, they will recalibrate it again and recalibrate it again and recalibrate it again. And this is also kind of a painful part. So superconducting qubits, they are very limited in terms of what they can do. And to perform a T-gate, kind of the one which allows you to run arbitrary operations in general. So you will have to build what's called the magic state factory. So on this particular picture, you see the orange one corresponds to your kind of data qubits, which you do some computation on. And those dark green areas are factories, which only task is to prepare the particular state, which then will be channeled by these light channels. So this is a chip, right? And you see that this part is actually corresponding to your qubits, which you want to use for computation. And these are kind of supplies to run the operations. And you just proceed generating those states, because those states are needed in abundance. You need a lot of them to do a kind of a reasonable computation. And it's kind of another problem that superconducting chips are actually require a lot of space. So how do companies deal with this? So in the latest paper, Google introduced the one about the Willow chip. If you saw the latest news, they made this 107, I think, qubit patch. So they introduced the idea of error budget. So the idea that they are trying to compute from the experiments what errors contribute most into their chips. And they, of course, will try to fight with the biggest contribution. So as you can see here, for all the platforms, for all the times, the most contributing part of error is a 2-qubit gate. So for superconducting, it's usually CZ or ISWAP now, so one of those gates. And this is the biggest part of the error source, right? So the next one probably is the idleness. So when you do perform a long operation, let's say a measurement or a 2-qubit gate, so the other qubits, they remain idle, they do nothing. So during this time, they decohere. They tend to have zero state in the end. So if you leave any qubit for a long time, it will in some time become zero. And there's no like fundamental way to do this easy. So if you make qubits wait, you will probably observe them all in zero state. This will be a source of errors. So then this one is about it's called the crosstalk. So if you have a chip, so when you do an operation between these two qubits, which are next to each other, so when you do an electric pulse into this area of the chip, it can propagate slightly to the neighbors of those qubits, and it can make some corruption to their states, which is called a crosstalk. So when they talk to other qubits are not addressed by the operation. This is also a significant part. The measurement is imperfect. You see, measurement is a huge part of problem. So in superconducting systems, leakage have 0 and 1 state, but the system is built in such a way that technically it doesn't disallow it to have the 2-state, 3-state, and on. So the way how they are built, they allow to have multiple states more than 0 and 1. So leakage is a source of error, and this is the part for 1-qubit gates. So this is the whole budget, and like Maria as a persona has to find her major challenges in this budget. So what is the scientist doing? Scientist who is aware about quantum error correction has to demonstrate the quantum advantage of those like soon coming devices, which will be using quantum error correction in them, which will be megacorp, giga, or teracorp QPUs, quantum computers. And they have to find this practical application, the algorithms. And it's very hard because on this scale, not many algorithms are actually useful. One of the huge problems in this world, in the world of chemical algorithms and like in general algorithm in the quantum computer, is that they don't have kind of a hard drive or a device which can store the data. You have to enter the data by encoding it there. So like if you were, instead of loading data from the file, write all these like values inside your program, right? The same you have to do with the quantum computer. You write all your values in your program. So and if you want to change, like keep the algorithm and change the data, you will modify the whole algorithm. You will replace the part related to data loading. And sometimes when I was doing research on this part may dominate in the circuit, in the program. So it will be the most significant part. And of course, it will accumulate a lot of errors even before you start doing computations. So one of the current hopes and like the technologies which is studied and improved is the algorithm called QSVT, quantum singular value transformation, just one of the algorithms which can help you to make this encoding less painful. And of course, if you do any algorithm in quantum chemistry, you don't want it to be just, an idea. You want to validate that what you actually did is a real working quantum algorithm. So you have to do validation, at least on a small model, on a small problem. And of course, if you try to simulate a quantum computer on a classical device, you will eat exponentially a lot of resources, right? So, and for Alexei, for example, he sometimes just eats 99.8% of all our company compute on the cluster because he's doing some simulation. And that's why he hates reboots, because his computations take weeks sometimes. This is an example of one of the papers, which was, again, trying to show how you can use different smart techniques. Let's say this one was about second quantization, to bring some of the problems down, right? So if you look here, you try to be in a reasonable time scale. So how many time will you spend on running the algorithm? And these are like models of some oxides. And you can say, okay, I want to move these numbers as low as possible for all this, like for number of physical qubits, logical qubits, and runtime. And quantization schemes, they allow to bring this down. Okay, so to bring the numbers down on those axes in all 3 dimensions. So what are quantum error correction researchers are doing? So you can actually split them into 2 people. The one is doing codes, and the other is doing decoders. But I joined them into Ophelia as a kind of a general representative for those. So, for example, when she thinks about, oh, there is a very good studied area of quantum error correction codes, which are called planar codes. They're very good for superconducting QPUs, and there are some ideas about how to implement logical gates. But the best way to implement a 2-qubit gate for these planar codes is to put them next to each other and make like pairwise qubits. But you cannot do this. You cannot just detach the part of the chip, move it close to another part of the chip, and make them collaborate. Instead, you have to find a smart trick, which is called lattice surgery, which have to like use an kind of a redundant part of the chip, so like more space to introduce a 2-qubit gate. For QLDPC codes, which are quite fresh and they are very like they're denser, they are more promising in terms of like how big is redundancy, so they are not that redundant. There are not yet a theory which is implemented to do logical gates. So you can build a qubit. You say, oh, I can preserve it in the state 0 or in the state 1, but I have no idea how to like implement an X gate on it. So I have a code, but I cannot use it. So there are different types of noise, and these types of noise are sometimes just killing the benefit. So for theory, for example, if you take some codes, the leakage noise can be very destructive for them, and you have to find, for example, wiggling circuits and wiggling codes which can fight leakage better. So when you have erasures, when you lose your qubit, then some codes are just useless. And if you take the classical, like theoretical, let's say, rotated planar code and try to run them on an ion trap device, you will find that shuttling of qubits, when moving the qubits around, spending time on moving them, can kill the benefit, because the shuttling time will mean, as you remember on the picture, that other qubits are waiting, they're idling, and they can accumulate the error for waiting. And shuttling just makes the program longer and accumulate more errors, and which kills the benefit from the algorithm. So when you try to run those algorithms on real physical devices, they all like sometimes just slightly unsuitable for some types of devices. And you have to find which codes map which hardware the best. And then when you want to handle a single logical qubit, which can be 1,000 of physical qubits with a decoder, you know what to do. But when you want to handle 1,000 logical qubits, it's kind of a very hard engineering task. It's how do you make them even sit in one fridge? Probably you'll have to do multiple quantum computers and make them communicate through optical cables. And yes, so the current challenge, which is, I think, underthought in the community, but it's already addressed, it's the compilation. Because you will take the logical program written by Alexei and try to run it on a physical computer, but you have to come from the gates applied to logical qubits and unwrap them into these patches, these error-corrected primitives, and make them work in the physical computer, in the control system of this QPU. And this will be like a much bigger program, because instead of having 1 qubit, you have now 100 of qubits, and your program becomes 100 times wider, and it becomes like maybe hundreds of times longer. So this compilation is a very tricky part. So these are examples of how the program look like. So these are the patches, this is the time dimension, and this is a 2-qubit gate, for example, between two qubits. Or this, for example, is called a stability experiment, when you have a qubit here and you want to teleport it in the other place of your chip. And this is the way how computations are done. It's all very complicated. They did it with Rigetti, like my Riverlane colleagues, and they could run this on a real physical device, and they could demonstrate that quantum error correction can be done in real time on a real quantum computer, which was an amazing result, because it was the first kind of integration test. So between the theorists who do quantum error correction and like practitioners who do quantum computers. And let's take the control specialist, Doğan. He builds control systems, and he was just told that he has to do a mid-circuit measurement. And he never thought about this because the whole design of control system was built with an idea that you will do a readout in the end. So you have classical data, and then you collect it from the register on the device. You read it through some like protocol. But now you have to stream the data. You never thought about streaming the data during the execution. And then he's told that not only mid-circuit measurements should be done, but also resets should be done. So you have to reset the qubit state to 0 in the middle of the circuit. And this operation becomes quite I will show you the slide, a very complicated one. And then it says that, oh, now actually we have to change the native gates. We don't run a CZ anymore, we run ISWAP. Can you implement ISWAP with your control system? Can you now send a different sequence of pulses? Is your control system flexible enough to implement like arbitrary gates? And of course, when you do like a superconducting chips, you don't read a single qubit. You usually read out them like multiple qubits because you don't want to have multiple wires in the fridge. You want them to sit like 5 qubits on a single wire, for example, and so on and so on and so on. So I won't even like speak about all the challenges control system engineer has. So speaking about like probably the question about why it's hard to implement mid-circuit resets and measurements. So measurement usually is assumed to be measure and reset. So when you say I want to measure state of a qubit, I assume that I measure and then I bring it down to the state of 0 in the end. And if you look at this graph, you will see A, B, and C. And you will see this A, B, and C here. This is amplitude and frequency of some pulses you apply to your qubit to get reset. And this is the kind of 0 is 0 state, 1 is 1 state. This is how you drift from 0 to 1. This is the time dimension. And you see that if you are here, the frequency is here and the amplitude is small, then you can allow it to decohere like freely, and it will take more than 1 microsecond, and it will still be in some superposed state. So if you want to make it faster, you find this kind of B point, and you apply those frequency with a particular amplitude, and you make it decohere in half a microsecond, 500 nanoseconds. And just to keep in mind that the gate duration, for example, the Hadamard gate or an X gate, is an order of 20, 30 nanoseconds. So it's one order faster. But if you want to make it very quick, like here, so you can apply a stronger amplitude on a very comparable frequency, but you will have a problem with the control equipment because here you have to catch it very quickly. So this one is 30, 40 nanoseconds. And if you do slightly more, you will raise again higher. If you do slightly less, you won't reach the desired state. So you have to be very calibrated in this operation. So it's very hard to achieve this particular duration in your system to fall into this sweet spot when you can reset a qubit in the same time you do for normal gate. And then it comes to, for example, the real implementation, which says, oh, actually, we have a control system which has a range of frequencies up to 200 megahertz. So we don't have this one here, right? So we never thought about resetting the qubits because we just read in the end. And then we allow them to decohere themselves, right? They just decohere themselves. And our control system has frequencies up to 200 megahertz, which means that this area is just unreachable for a quantum computer, which was built with an idea of NISQ in the head. So what you have to do a reset, you have to rely on the second order, which is even you see, it's thicker, it's very hard to get there. And you have to find for this probably B as the most reliable part here on the second strike. And the quality of this operation will be way worse. And having those resets is essential inside quantum correction circuits. But some devices are just incapable of doing them in a right manner. So probably a very hard topic, but for people thinking about QC, one is a quantum chemist, or maybe it's a government spy who is interested in cracking the RSA code, or maybe it's like a currency trader who wants to benefit from quantum computers. This is a QC expert who builds the codes and decoders. This is a control expert who is now exposed to different challenges, to being able to run resets, measurements, different gates, which he never, like she never run before. And then the qubit experts has to move down by the physical error rate to make devices more like scalable in QEC world. So there are different error sources in qubits and control systems which we have. And there are multiple, and they are specific to platforms. You have superconducting, atoms, ions, photonics, and they all have their own sources of errors. So QEC is not only a scientific discipline, it's also an engineering discipline. So you have to do devices, make devices and write code which is specific for platforms. It should be specific for noises, for different speed of QPU. For example, if you think about doing a superconducting computer, there is no other way except doing it in hardware in ASICs. If you do ion traps, you can still benefit from running on GPUs. So the latency is kind of okay, but kind of you have pros and cons in both. So doing hardware is much harder, but kind of superconducting systems are the most scalable ones. So you can do hundreds and thousands of qubits already. And yeah, so as I mentioned, control systems are affected by QC requirements. Whew, deep breath. Your questions, comments?
Yes, please, questions.
Can I have a question?
Yes, sure.
Yes. So I just want to ask about codes like Shor's 9 or 7 qubit code or stabilizer code. So it seems they're not used in practice. Is it only a theoretical concept?
Once again, which code?
Shor 9 qubit code or Gottesman stabilizer code.
So I would just make a remark that I'm not a QC scientist, I'm an engineer. So I can be saying wrong things in terms of theory. I don't want to say wrong things. So what I understand, and probably like there are some slides here, is that there is an area of code which is called the stabilizer codes.
Yes, that's
yeah. So these codes,
stabilizers.
Yes. These codes are based on the idea that there is an operator called stabilizer, which works as a parity check. Right. So, and among like within this area, there are some codes which implement the concept. And for example, like planar codes, rotated planar codes, toric codes, repetition codes, they are all stabilizer codes. So these are like subsets of this like idea of stabilizer codes. They, in general, they're all stabilizer codes. Some of the codes they use like other techniques, which I'm unaware of. I know that they do exist, not only stabilizer codes exist, but like in the area of stabilizer codes, these are like subdomains which you study.
Mm-hmm. And did anyone implement, or is maybe not even implementable, Shor's, let's say 9 qubit code, or is it just pure theoretical value?
I'm slightly confused because I probably this is the term which you use has a synonym which I know. So if you let me Google.
Yes, Shor's 9 qubit code.
Shor's 9 qubit code.
Because it's a big in the theory. You know, I'm more in theory. I would like to be a little bit in practice, but okay, it doesn't matter. So
yeah,
just,
I mean
just
star-shaped tree graph. Concatenation qubit phase flip with a bit flip. So it's kind of some combination of repetition code and something else.
It uses nine codes for 9 qubits for one logical qubit. So
yeah.
it detects flip error, and it detects actually it can detect one flip error and one phase error.
I would say that this looks like an interesting kind of playground for like starting devices. So I'm not sure about the connectivity required here. It might be
It requires a lot of qubits. I mean, it's 9 qubits, and it requires actually a lot of gates.
No, I mean, if it requires a lot of like connectivity between those qubits to run gates, then it might be a tricky part because only ion traps and neutral atoms can run those. So I think that what is actually currently used as a playground for very like early devices is just a repetition code, this one, bit flip repetition code, which is less capable because this one can account for 2 types of errors, and repetition code can only pick one. It can either pick Z or X
So
error.
most of these codes are basically like a bit flip codes, or
So
they also detect phase flips.
So let me probably like move to the next topic, and I will show you how they combine those two. Okay.
Oh, okay.
Okay. So again, I'm here representing an engineering function, and I don't want to like say very wrong things. I'll only speak in the area of my expertise. So speaking about theory, so this kind of the stabilizer formalism is the formalism which says approximately the following. So if you take the kind of textbook on quantum computing by Niels and Chang, you will see that if you take the quantum computer, a significant part of errors can be modeled, like approximated, with a combination of 2 types of flips, X and Z flips. So it doesn't mean that this is what actually happening in the quantum computer. But if you run a quantum error correction circuit, the outcome of those errors and the outcome of the real physical system running will be the same, right? So here on the graph, you see that the Google has its own library called STEAM, which can only do like Clifford simulations. So, and they can only do this Pauli noise, which is X or Z flips. And you see that these curves, like the dashed ones, the dotted ones are simulations, and the solid ones are real experiments. And dotted lines are slightly below, which means that they account a big part of the error which happened in the quantum computer, but not the whole part, right? Not everything. There is some lack of modeling. So because there are other types of errors. As I mentioned, there are like leakage errors, which are very hard to simulate in this way. There are some other types of errors, which are not like Pauli errors. And there's also like if you take a decoder, for example, it can also account for the fact that X and Z can be correlated. They can happen at the same moment, which is a Y error, but some of them don't care about this. And stabilizers are such an operators which anti-commute with those errors. So which means that if you pull the stabilizer through the error or error through the stabilizer, so it will create a bit flip, right? So the minus will appear in the end. And like this picture will show you how it looks like. So what we have some types of errors which are like in real physics. Then we have a model which says, oh, these all errors may be with a high precision approximated by just X and Z flips. Then we will introduce those stabilizers which will guard our parity. And then what happens with those like stabilizers? They report us particular probable errors, right? They say 0 or 1. Did the parity change or not? Not all physical errors can lead to a flip of a logical value of the qubit. So it means that if there's some flip happened, some error happened, it doesn't mean that we just have to run and fix it. It might be like a bearable error we can survive for a long time. Then if you have a logical flip, so it means that the logical state of your qubit changed. You had 0, now if you read the state of the logical qubit, it's now 1. So you flip the logical, the big patch changes the value. It doesn't mean this is an error, because if you can detect it, you can correct it afterwards. So it means that the error is something which you didn't detect. So something happened to your qubits, but you didn't notice this based on the codes. So the easiest way to obtain such an error is the chain which touches the boundary of your patch, and it changes the state of the logical qubit. And that's why you have this idea of code distance. So if you make the patch bigger and bigger, the chain should become longer and longer. And the probability of such a chain exponentially decays because the probability is small. And to have the chain, you have to have a multiple of those probabilities, which is exponentially small. So if you look at this diagram, so I think the question was, how do we detect for X and Z flips at the same time? So let's look at this, like I call it a patch. This is a combination of qubits. So white ones here are data qubits. So there are 9 qubits which are holding the state. They all should be, let's say, all zeros to be 0, all ones to be 1. And we have those ancillary qubits that sit in the middle. So this code is called rotated code because if you want to put it on the device, you have to rotate it 45 degrees to create this like grid, right? So this is the line, this is the line, and these are like vertical lines, for example. That's why it's rotated. Like on the physical device, it will be 45 degrees rotated. So what happens is that you allocate some of those to guard for X errors and some of them to guard for Z errors. And each qubit here, here, here will be involved into multiple stabilizers, multiple this like parity checkers. So for example, this one touches these 4 tiles. 2 of them are a parity check for Z flip. 2 of them are parity check for an X flip. Sorry. So this is the circuit which you already saw, like one of the variations. So it's a Hadamard gate which puts the ancillary qubit into superposition. Then you do a parity check with C0 here, which means that, for example, for this one, we'll run C0 there, 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 and there. Those qubits will report. And then we like move back to the computational space and measure and reset. And we observe whether bit flip happened or not. At the same time, these 2 qubits are involved in this checker, parity checker. And the circuit for them will be slightly different. They don't have Hadamards here, for example, on the sides. And they will observe for Z flips. They will try to seek for Z flips on those qubits. So these 2 qubits will be checked for X flip on this and this, let's say, checkers, and on Z error here and here. That's why in total, when you run the whole circuit, the quantum error correction circuit, it runs the checks for both types of errors for data qubits. I think that at least partially answers the question, so how do we check for both types of flips? Yeah, so when we speak about measuring the logical state of the qubit, usually for these types of codes, you say the logical state of the qubit. You don't have to read all of them, but you can read one like stripe, one line of those to obtain the measurement value. Say the XOR of those values will be like 0, 0, 0, XOR 0. The logical state is 0. For different codes, it might be different. It's not exactly the same that all zeros or all ones correspond to 0 and 1. So what do we do then? So if each of these like colored qubits report us a bit of information here, so if we do a measurement, so you, after the execution of those circuit, which is, as you see here, around 1 microsecond, 1,000 nanoseconds for this paper. So you collect those from one round of experiment, and this is called a syndrome. So it's kind of, if the device is ill, you collect some evidence about its sickness, and this is called a syndrome. So if the detector changes its value, so it was like 0 here, it became 1, you see a red dot here, okay? So if it happens like this, so if sorry, I have a chat. Okay, so there's a link here, okay. So if this changes the value and this changes the value, what might be the particular reason for this? The reason is that the data qubit between them might experience the bit flip, right? So it has X on it, and it changed the parity checks on both neighboring detectors, right? And this is what's called an edge, and these are vertices. And sometimes you can have like an error happening during the quantum error correction round. It's called a hook. Sometimes your measurement may be wrong. So if your qubit did flip, the detector flipped, but nothing actually happened to the neighbors just because the measurement was done wrong, This can be a measurement flip. And these all are different types of reasons to have kind of changing of the state of the syndrome. So your syndrome changes with time, and you try to guess what might be the reason to have this change. And if you think in terms of the problem, of the mathematical problem, so you get those like red circles as an input, right? You say, I have bits of information where I observe some parity checks being one or changing the state. And then I have to come up with the best suitable matching of those bits in a graph to be kind of most probable. So what was the most probable combination of X flips, Z flips, these hooks, these measurement problems, if I observe those syndromes? And this is the classical algorithmic task. And even the most like prominent algorithm in this area called minimum weight perfect matching, so MWPM, implemented in the PyMatching library, which is basically like the name of the algorithm says what it actually does. It tries to find the matching for those syndromes with minimal total weight. So then we ended up with the decoding problem. So what do we have currently in the space of decoding? So as I mentioned, the best known, the default algorithm is MWPM, minimum weight perfect matching. So it's the best algorithm if you run it on a classical computer. So you don't put it into an ASIC or you don't want to run it on a GPU. So it's the fast one. So it only accounts for uncorrelated X and Z errors. So if your device has a Y biased noise, so if your qubits can experience those flips, there's a high chance that it won't detect them or won't understand them correctly. And this is kind of a default choice to start exploring decoding. So currently it has some different interesting fixes. For example, you have correlated decoders which try to account for Y errors. You can do it in 2 passes. You can do it pre-decoders. There are some approaches to make it better, but the algorithm itself is fast in terms of implementation, but it scales not very well. So on one kind of, if you take the one extreme of the computation, if you speak about quantum error correction, the best performing decoders are based on tensor networks. These are or machine learning decoders. They are very like connected areas, and they can learn perfectly the model of your noise, but they're very slow. You cannot put them into a real system because they scale very badly. On the other scale of those, if you want to do fast and you probably don't want to have the best quality of decoding, but you want to have the decent quality of decoding, you will go to something which, like in the literature, most I think famous algorithm is called Helios. It's the massively parallel decoder. So Riverlane has its like own competitor called LCD, local clustering decoder, so which we put into hardware and made it work on hardware. So it can actually decode very quickly, and it scales very good because it has only local connectivity. So you can basically extend it as much as you can for any problem. And if you want to switch like in a research area and say that these are extremely quality, these are extremely fast. And what are these? Other decoders are exploring the potential because these decoders, they only work with the model which we just discussed, the model of X and Z errors. So they can only assume that these errors exist. But you remember there was a gap between the dotted line and the solid line on the Google plot. So the model is not perfect. So can we make this model better? And here we have multiple ideas how to incorporate our knowledge of physics into decoders. For example, we can do decoding of soft information. What is soft information? In fact, when you measure a qubit, you don't get 0, 1. You get either some, if for ion traps, you get some number, how the amount of photons you captured from the camera. Or if you do a superconducting qubit, you have the two-dimensional plot with frequencies. And these numbers are very useful. They bring much more information than actually 0 and 1. So you can try to involve these numbers, which are real valued numbers instead of like integers, and try to decode with them. And our research shows that yes, you can. So and then we can try to propagate those methods into like Helios style decoders into LCD and make it work there, right? So because it will be even more quality decoder, right? So the leakage noise is also the one which is not accounted by those models. Leakage noise is not X and Z flip. It's you move from the computational space. You do computations like they corrupt the qubits, and in this way you have to account for this noise. And there are algorithms and there is implementations of LCD decoder which account, right? So which can do decoding of these types of errors, and which can bring down again the bar, so it makes the logical quality of qubits much better. And just to finish in the whole like mess of this problem, so what other challenges do we have? I already mentioned that in the current area, in the research, we mostly care about being able to implement logical qubits. So currently we struggle to do a single one in real life. And we only run the experiments which are called like stability experiment or quantum memory experiment, which are like literally like identity gate, doing nothing, right? So waiting for a long time and making sure that the qubit survived in the same state it was before. So if you want to do 1 or 2 qubit logical gates, we have to do lattice surgery. So we have to do these weird operations on the lattice, like have to move those patches around or have to glue them together. And this is like extremely complicated circuits just to do a kind of a CX, for example. But even in this case, you will probably sit in the Clifford space. So if you do this lattice surgery, you will be able to do Pauli, Hadamard, S-gate, CX, something missing. You cannot do anything with those gates because these gates, this set of gates, is classically simulatable. So you can simulate them on a classical computer at the same pace, or the same speed. So why would you bother? So you need something more. You need to implement T-gate, the square root of S, to make your computer like a universal quantum computer. And as I mentioned, this is, for example, how would you implement this Toffoli gate, right? Toffoli gate needs these number of T-gates, right, to get there, right, to be decomposed into something like primitive. And here you see a circuit which allows you to run a T-gate, which actually says, oh, to run a T-gate on my state, prepare some state, apply a 2-qubit gate, do a conditional measurement, and then apply fixes. And this will be kind of your equivalent of applying a T-gate. So it needs kind of a supply of what? Supply of a state and a small circuit to perform this gate. And here you see what is called the magic state factory. So it's the kind of circuit which produces T states in the end. So this one out of 15 will be the state you need. So you will waste like 15 qubits to get one with the desired state. And these are actually nested. So sometimes there are 2 or 3 levels of nestedness to perform those T gates. It's all very, very extremely greedy for space on your chip. And these are like the screenshots which show you how the allocation can look like. These ancillary qubits to allow communication between these. So these are like factories and they're connected to the logical qubits. You have to keep corridors between them to apply 2-qubit gates. This is all very, very, very greedy for qubits. So speaking about this part, like we dived into theory, and I think I'm overrunning in terms of time already. Sasha, please stop me if I'm doing something wrong. So we have the problem of quantum error correction stated as a classical problem. So the input for decoding is called a syndrome. It's a collection of evidence, parity checks, which you collect from the circuit. So from those like mid-circuit measurements and reset, which I mentioned in the beginning. So they can account, some of them account for X flips, some account for Z flips. And then you try to restore the most probable picture. So it's like you're looking at the clues and you try to see what happened to your quantum computer between these 2 rounds of measurements. So decoders are algorithms, the classical algorithms, which take those syndromes and try to find what was the corruption. and did the logical value of the qubit actually change? Did it change? And then they should be very fast. That's why some of them can only run on a kind of on a hardware, on the ASICs or FPGAs, while for like ion traps, probably you can still survive with GPUs. And if we speak about, in particular, about superconducting qubits, they cannot be useful without having T-gates. And T-gates are produced by magic state factories, these parts of chip, these areas on the chip, which prepare you like a single qubit with a high fidelity T state. And then you can perform a T-gate. That's why if you look at the circuit here, which I showed you, so you have to have a supply of those T states at almost each iteration. That's why you need multiple of those factories, which will be giving you those T states when they need it. And still the question, are we going to get there? Are we going to build a quantum computer? And I think as a person who is working for a quantum computing company, my answer is yes. I have 3 evidence why it's doable. So one, that the theoretical basis is very strong, and we have all parts of the work of the system working separately, sometimes joined into small like projects. So let's say you have someone does qubits and control system, and then we come with codes and decoders, and we can solve like these like first 4 items in a single box. So we do have these experiments running. So some work is done here and here. So there are logical gates which are compiled into distributed decoders. And this is also like, so at one moment we will glue all these 6 points together, but currently we do have aggregated solutions of 3 and 4 of such elements already. So the companies who are doing research, they are very focused because they won't survive without building this. And this makes them collaborate, especially keeping in mind that how business and government states the problem. So they say, give me a quantum computer, right? And show me this is a working quantum computer. So we'll have to build a system which will have all of these all together, and we'll run some program, right? In the end, that's what DARPA does for US, which was MQCC does for UK, the UK. So they do like a similar project. They buy quantum computers. They don't care, like they care, of course, but they don't want you to show performance here or show performance here. They want you to show the performance of the whole system. And that's why the companies who were originally built, they keep it in mind that, oh, we will build a quantum computer. And like in a couple of years, they realize they can only build qubits, but not a quantum computer. So they are now tending to collaborate. They meet each other and say, oh, please, I will buy your part of the solution to put into my part of the solution to make it work together. We actually can call it a quantum computer now, right? So because just qubits are not enough, just control system is not enough. So companies do collaborate, and you like currently I experienced the stack of like 3 companies in a row. So we are doing error correction, the other company is doing control system, and the other company is doing qubits. 3 different companies, and only in this combination they can be called a quantum computer. And yes, so I think this was the last slide, and this is the space for questions. So the QR code here is the link to QC report. And also I think this link is also in the chat of this call. So my Telegram is just Protasov, and the same, you can write me an email to my work mailbox. If you have any questions, I don't have anything to say, please ask me questions.
I have a question, if you don't mind. As an engineer, I have not seen any program written in quantum that would be useful. And you're an by the way, like this is the first quantum talk that I really enjoyed immensely, maybe because we are engineers like each other. But okay, fine. So we're gonna build a quantum computer and everything. What's gonna run on it? I have not seen a successful algorithm out there. I know they talk about machine learning and things like that, but do you know of any successful algorithms that are waiting for that quantum computing?
It's a very good question. because as I said, okay, there's one persona, which Alexei, who is writing, like trying to find the algorithm which will actually run on the near-term quantum computer. So one thing about quantum computers is they're like the obvious thing about them is that they are naturally quantum. So and it means that the tasks which are naturally quantum are the most suitable tasks. I think Richard Feynman, like in 1980, was the person who said, "Oh, actually, the quantum computers will be useful to simulate quantum systems." And when it comes to quantum systems, so what I can name, these are proteins, like folding of proteins, like trying to estimate what will be the configuration of the protein when it folds. So, and how, for example, which parts of the protein will be looking outside, which will create the medical properties of the drug, right? So you have some drugs which have proteins, and you see which active parts will be in this protein when it folds. So you can, let's say you come with a candidate molecule and say, this is the molecule, I want to see how it will fold. And this problem is also already solved by AlphaFold, right? From Google, from DeepMind, and which is a kind of a competitor, right? But quantum computers, they promise to be like 100% accurate here. So other chemical systems are grids, like crystal grids, for example, like oxides or metals. And again, so what we want to know, some chemical properties of those, some chemical properties which can be derived by physical computations. And what I know, again, so there are some projects where the companies who are like automotive and aircraft companies who want to know, can we use quantum computers to assess the properties of potential catalysts, katalysator in Russian, the thing which makes the reaction faster, right? The chemical reaction faster. So what they do, they want to simulate the properties of these crystal grids. And the examples which I showed you, like on the picture, the plots which Alexei did with the second quantization method, were exactly for the oxides performing like catalysts in some particular reaction, and to see what will be their chemical properties as a catalyst here. So this is again like very naturally quantum problem. So the crystal grids are atoms, their relations between each other, and I think this in general quantum chemistry, right, is I think the major area. If you look at like each and every company who does quantum computing, they are scientists who are not actually building the qubits. They most probably will be working on those algorithms, the algorithm of quantum chemistry, different applications of those, because these are the closest possible candidates to run a quantum computer. If you move to the next level of consumption, of course, everyone is saying about RSA. So it's like, oh, if you have kind of a few thousands of qubits, then we will be able to run the Shor's algorithm or some modification of Shor's algorithm, and then we'll be able to decode RSA. Cryptography. And kind of some people can be very skeptical about this, but if you look at those who give money to research, these are DARPA, all the like actually military research, like if you have a rich country, let's say China, these will be most probably their interest. They don't care about like, protein folding that much. What they're interested in being able to decode cryptography, especially the one which is already like you have encrypted drives, for example. You don't have to catch the message. You can take the drive which is encrypted and being able to decrypt it with an algorithm. So these applications are, I think, the next level. But they are more like in terms of TerraCoop, if you look at the scale, they are less close to current time than chemical applications.
Stanislav, well, thanks a lot for this beautiful lecture. I think
Sorry for overrunning
a lot. I wanted to ask, I mean, you mentioned that we can share the slides. Is that okay?
Yes, of course, yes.
Okay, so I prepared here, and I'm going to share them through this chat window. So
okay.
Just everybody who participate in this call, you will be able to download.
Yeah. As you will see, like most of the reference there are just to public papers, to Nature or to arXiv. So it's not nothing I reference from kind of private. So it's all like I think that what was interesting that the area of quantum error correction and quantum computing in general is very like demanding. So it requires you to learn a lot. And without being inside, it's very hard to learn all this everything and put them on the same like picture in your brain. And yeah, so being able to work here makes the picture kind of brighter and interesting. But at the same time, I tell you nothing like specific and like no secret. This is all like available online. Just have to know how to read the papers. And I think that the report which you mentioned and which is the link is there is a very good starting point to like glue together the quantum computing and quantum error correction.
Okay.
What do you make?
Recording.